In this video, I want to talk a little bit about the Pythagorean Theorem. And the Pythagorean Theorem has to do with right-angled triangles. So, I need to tell you about a couple of things about right-angled triangles, just so we have some nomenclature for the different parts. Obviously, a right-angled triangle, which we've learned before, is a triangle where exactly one angle has measure 90 degrees. And of course, it's only one angle. You can't have two 90-degree angles in a triangle being 180 degrees, since there are 180 degrees inside every triangle is the sum of all the angles. So, the important things for us are the different sides. So, we call the sides that are attached to the right angle, we call those the legs of the right angle triangle. And the other side, which happens to be the longest side, that's across from the right angle, we call that the hypotenuse. So, the Pythagorean theorem states that if you have a right angle triangle and the legs have, say, lengths A and B, so let me give this leg length A and this leg length B, and the hypotenuse has length C, then it's a fact, and we're going to prove this fact, that if you square each of the lengths of the legs and then add them together, you get the square of the length of the hypotenuse. So A squared plus B squared equals C squared. And let's work on proving that right now. Before we start, I want to mention that there are countless proofs of the Pythagorean theorem. I'm just showing you one of them, but there are countless others. You can look them up online, look up proofs of the Pythagorean theorem, and you will find many of them to have a look at. So this is just one. I like it because it really relates the idea of area to the Pythagorean theorem. And if you're thinking of it, if you look back at the formula, a squared plus b squared equals c squared, remember, area is a two-dimensional measurement. So if we're raising things to the power of 2, you can think of us as squares where the side lengths are A, B, and C. So let's say we have indeed a right-angled triangle. And so let's say I started with this guy that I'm going to highlight in blue here. And it has lengths A and B for its legs, and the hypotenuse is length C. And we'll call the angle measures here 1 and 2. So what I'm going to do here is I'm going to build up the following figure. I'm going to make 3 other copies of it, and I'm going to attach them in a way that makes a square. So I'm going to arrange my 4 copies of the triangle so that each side has length A plus B, so there's an A here and a B here, and at the corners are going to be the right angle. So you can see how it's done here. And this is going to be the big square. We're going to call this the big square. So we're going to do this in parts. So the first part we just kind of talked about. So let's talk about a sketch of how this works, and then we'll show it in detail. So we're going to show that the big square is indeed a square. We just have to mention why that's the case. The next thing we're going to show is we're going to show that this diagonal thing that looks like a square is indeed a square as well. So the small square inside is a square. And then the third thing we're going to do, once we do that, we're going to calculate the area in 2 ways. And then simplify to obtain what we want, which is a squared plus b squared is indeed c squared. So that's our plan of action here. Okay. So let's prove this then. So let's prove part 1. Well, the big square is a square since, well, each side length is the same. Each side has length a plus b. And each angle here is a right angle. So by the way, we constructed this by, let's say by construction. That's probably a better wording. By construction, since the big figure has all sides of length a plus b and all angles being right angles, it's a square. Excellent. Okay, so we know that this big figure is a square, which is great because we know how to calculate the area of squares. Now, to show that the small square is a square, well, all sides have length c, but remember, for a square, you also need all angles having the same measure. In this case, it'll be 90 degrees. So we need to show that. Let me scroll down to make a little bit of room. And in fact, maybe I'll make a copy of this and take it with us. Let's see if I can do this. There we go. I'll have to erase that a squared in a second, but I can do that. Let me scroll here. Okay. So I just moved this so we have a little more room. Let me erase this. Perfect. Okay. So, now part 2, we need to show that first of all, that angles 3, 4, 5, and 6 in our diagram, which I will just write in red since they're given to us in red in the diagram. So 3, 4, 5, and 6 have measure 90 degrees. Okay. Now, remember that this is a right angle triangle. It's a right angle, so one angle is 90 degrees, and it's a triangle. So the sum of the angles has to be 180 degrees. So in our right triangle, we know that the measure of angle 1 plus the measure of angle 2 plus 90 degrees, so that is the measure of angle 1, the measure of angle 2, plus 90 degrees, has to be 180 degrees since it's a triangle. And if we subtract 90 degrees from both sides, we get that the measure of angle 1, oh, let me do this in black actually, the measure of angle 1 plus the measure of angle 2 is 90 degrees. So we don't know exactly what these measures are, but we know they have to sum together to give you 90 degrees, since here's the other 90 degrees of our triangle. But remember, all of these angles here that are labeled 2 are congruent, since they're just copies of the same triangle. So let's scroll up here. So consider this yellow part here that's shaded in. So let me write that. Consider the yellow arc. in the diagram. Arc. There we are. Well, we know that angles 1, 2, and 3, these guys are supplementary. So we know that angles 1, 2, and 3 are supplementary since they break up a straight line. So let me erase this comma. That's not doing anything there. We know that they're supplementary, so what does that mean? So it means that the measure of 1 plus the measure of angle 2 plus the measure of angle 3 has to be 180 degrees. But, hey look, we know from above that I'm double underlining in blue here, that the measure of angle 1 plus the measure of angle 2 is 90 degrees. So I know this is 90 degrees. So 90 degrees plus the measure of angle 3 equals 180 degrees. Here's our 90 degree here. And subtracting 90 degrees from both sides, we get that the measure of angle 3 is 90 degrees. Maybe I'll put in that subtraction. So we subtracted 90 degrees from both sides. And we could do the same argument for angles 4, 5, and 6. So similarly, for 4, 5, and 6, we know that the measure of these angles, well, let's even put an equals the measure of angle 5 and equals the measure of angle 6. They're all the same. And we know what they are. They are all 90 degrees. So that's great. We know all of these angles inside here that I'm circling in green. All these are 90 degrees. To reiterate, we know that angles 1 and 2 are complementary angles. They sum to 90 degrees. So since these angles are supplementary, all three of them break up a straight line, angle 3 must be the remaining 90 degrees since we already have 90 degrees. Okay, so we pretty much have part 2 done. We have a figure that has 4 sides. All sides are the same length, and every angle in it is 90 degrees. So since, let's do this in black. The small figure in the interior has all sides of length C, so they're all the same length, and all angles being 90 degrees. It is a square. So we know that. That's great. So let me scroll up again just to kind of reiterate what's going on here. So here's our figure. We know that this here is a square. That's what we just proved in part 1, which is very easy. We just had to write it down. We know this bigger figure is a square. Now, if we wanted to calculate the entire area of this bigger figure, well, we could do it in 2 ways. Well, it's a square, so we can just use the formula for area of a square to calculate its area, side length squared. But we also broke up this figure, this square, into a smaller square with 4 of these triangles. It's broken up into those pieces, so if we add the area of those pieces, we should get the same result. So they should equal. It should equal the area of the square with side length a plus b. So that's part 3. We're going to equate those areas and do a little bit of algebraic manipulation and show that a squared plus b squared must equal c squared. So this is part 3. We're calculating the area in 2 different ways. So we know that the area, I'm going to write it like this, the area of the big square is the same thing as, well, the area of the small square plus 4 areas of those triangles above. So we know the formulas for all of these things. So the area of a square is a side length square. The big square had side length a plus b. So this is a plus b squared. That's the area of the big square. The area of the small square is c squared, since the side lengths for a small square were c. And we have 4 times the area of the triangles. And the triangles had a base of a height of b, so it's base times height, divided by 2. Remember, our triangles looked something like this. Here's our right angle, this was a, this was b, so here's our base, here's our height, or the other way around. You could just lie it on the other leg if you like, if you wanted to flip what the base and the height were, but it wouldn't matter. Okay, so we just need to simplify this and see what happens. So a plus b squared, I need to square a plus b, so it's a plus b times itself. And we just do the distributive property, multiply every term in the first bracket by every term in the second bracket. I'll do this quickly, but you can check it as an exercise. You'll get a squared plus 2ab plus b squared. So we know that is the left-hand side. A squared plus 2ab plus b squared. Okay? And the right-hand side is c squared plus, well, we have 4 times a times b over 2. If you like, you can think of this as 4 over 1. And you could say, hey, look, here's a common factor of 2 that'll cancel out, 1 in the denominator, 1 in the numerator. So this ends up being 2 times ab over 1 times 1. So we don't need to worry about the denominator since it's just 1. So this is just 2 times a times b, 2ab. So the left-hand side simplified to a squared plus 2ab plus b squared. The right-hand side simplified to c squared plus 2ab. But look here. Both equations have this, or sorry, both sides of our equation have this term of 2ab. So remember, I can do whatever I want to an equation as long as I do to everything on both sides. So I'm going to subtract 2ab from both sides, and equality will still hold. And what do I have on my left-hand side here? I have a squared plus b squared. And on my right-hand side, I just have c squared, which is exactly what I wanted to show. And we're done. A quick recap of this, just to make sure we all understand. Let me scroll all the way up. So we wanted to prove that a squared plus b squared equals c squared. If we had a right angle triangle, then a squared plus b squared equals c squared. So we started with our right angle triangle, and we built this diagram. We know that the outside figure, the large figure, is a square, since all sides have length AB, and all angles are 90 degrees. The smaller figure is indeed a square as well, because, well, all sides have the same length. In fact, that is C, and all of the angles are 90 degrees, since we know that the sum of angles 1 and 2 have to be 90 degrees, since they're the other angles in this right angle triangle, and these all have to add up to 180 degrees. Well, if these add up to 90, and this has to be 180 degrees, since it's a straight line, this has to be the other 90 degrees. you can do that argument exactly the same for 4, 5, and 6. So we know that this is indeed a square as well. Now that we know that those figures are indeed squares, we just calculate the area in two different ways. Just the area of the square entirely, and then the area of the pieces we broke it up into. So the 4 triangles and the 1 smaller square. And we scroll down. And so we just write everything down and just algebraically simplify. Area of the big square is a plus b squared. Area of the small squared is c squared. Area of the triangle is a times b over 2. And we have 4 of them, so it's 4 times that. Do a little bit of simplification. We notice we have a common factor, or a common term of 2ab on both sides. We subtract it off, and we're left with exactly what we want. So that is the proof of the Pythagorean theorem, or I should say a proof of the Pythagorean theorem. There's loads of others out there as well, but again, I like this one because it's fairly geometric, and you can really see what's happening. So we know for right angle triangles that, in fact, let me write right here. We know for right angle triangles that a squared plus b squared equals c squared. So this is a, this is b, and this is c. We know the Pythagorean theorem holds. But what can we say for acute and obtuse triangles? So let's explore that. So remember, acute triangles are triangles that have an angle that have all angles, I should say, that have measures less than 90 degrees. So just to kind of illustrate what's happening here, what I'm going to do is I'm going to take this side A and I'm going to rotate it so this angle is less than 90 degrees, but I'm going to keep the same length for A. And I'll do this in the color blue. And again, remember, this is just a sketch, so it might not be completely correct, but imagine that I'm taking A here and I'm rotating it. So I'm rotating it that way, but keeping it fixed here. So let me do that. And it should roughly look something like that. I'm just rotating side A. Well, what happens to side C if I do that? Well, let's see. Well, it still needs to make a triangle, so it still needs to be connected to each end. And you can see here that, oh, that's not very good. Let me draw that a little bit better. You can see that C has gotten shorter. So as I rotate this side A, so that this angle here is less than 90 degrees, it makes the hypotenuse shorter and shorter and shorter. So, how does that play out in the Pythagorean theorem? Well, we're not going to prove it directly, but hopefully this kind of intuition helps you figure out what's going on. But if C gets shorter, then A squared plus B squared is going to be bigger than C squared. And again, I just want to point out that really a hypotenuse you can only talk about if you have a right angle triangle. So we'll just say here for all of these that C is the longest side. So whenever I'm talking about C, I'm talking about the longest side. In a right angle triangle, it is indeed the hypotenuse. In an acute or obtuse triangle, it's just the longest one. Okay. And what about for an obtuse triangle? Let's explore again. So I'm going to do the same thing. I'm going to draw a right angle triangle. There it is. And what I'm going to do, instead of rotating it so this angle is smaller than 90 degrees, I'm going to rotate side A so that the angle is larger than 90 degrees. Maybe I'll do this in red now. So again, I'm going to rotate it this way now to open up that angle, to make it larger. So maybe it looks something like that. So this is my new A, same length, I just rotated it. Now what happens to the side C to make a triangle? Well, if I rotate this, C is just joining up those endpoints. And you can see here that C has indeed gotten larger. So C is now longer. And if C is bigger, then its square is bigger. And remember, the lengths of A and B didn't change. The only thing that changed was the angle between A and B. It's obtuse now. It's bigger than 90 degrees. So for obtuse triangles, we have that A squared plus B squared is smaller than C squared, since C has gotten appreciably larger. So let's do a quick example with this, and we'll explore this in a little more detail in probably a future video. But let's do the following example. Let's classify a triangle with lengths. Let's say 9, 7, and 11 as acute, obtuse, or right. Okay, so all we need to do this is use our formulas above. Pause the video now, try it yourselves. It's not a particularly onerous exercise. Just check which of these equalities or inequalities is true. And remember, C is always going to be the longest side. Okay, now that you're back. Our longest side is, of course, the side that has length 11. So this is our C, and A and B are 9 and 7. Doesn't matter which is which. They're just the two different legs. So let's test. So 9 squared plus 7 squared. What is that? I'll use this symbol. I'll use a box to mean, well, it's either greater than, less than, or equal to. We don't know yet. 11 squared. And we know all of these. 9 squared is 81. 7 squared is 49. And 11 squared is 121. Again, if you don't know them, you can just do a little multiplication on the side to check. And 81 plus 49 is 130. And here's 121. What side is larger? Obviously 130 is larger. So since A squared plus B squared is bigger than C squared, the longest side, that tells me that this is indeed an acute triangle. So this triangle is acute. And that's our little check in order to do that.